So we already went through X-ray, we already went through CT scan. The next medical imaging technology that we will have to go through in your syllabus is something relatively new for 2022 syllabus. That one is positron emission tomography, or shortened as PET. Now in PET scanning, you need to use something called a tracer in order to generate an image. A tracer is just a substance containing radioactive nuclei that is absorbed by the tissue being studied. So what you would then do is that in PET scanning, a beta plus emitting radioactive tracer is used to stimulate positron electron annihilation in order to produce gamma ray photons. Okay, so your tracer that you use, that you are going to inject into your body, must be specifically emitting beta plus particles, so that later on you are going to get positron electron annihilation. So your patient is injected with a beta plus emitting isotope, usually is fluorine 18 or shortened as F18, so that your emitted positrons annihilate with the electrons inside the patient. So you look at the diagram below, this is your patient. What you do is that you inject a tracer that specifically emits beta plus particles. So the idea here is that once your tracer is inside your body and emits beta plus particles, it will actually interact with an electron and undergo something called annihilation. Okay, so the annihilation of the protons and electrons will actually produce for you two identical gamma ray photons that travel in opposite directions in a straight line. Okay, so the positron and electron, they annihilate each other, and then what you're going to get at the end is two gamma ray photons that travel in a straight line. Okay, when they travel in a straight line, that is known as your line of response. Okay, so what you want to do from there is then to detect these gamma ray photons that are emitted. The gamma photons are then detected outside the body by a ring of gamma detectors that surrounds the body that is being studied. So what you want to do now is that once you inject your tracer, once you have an annihilation, and then you get your gamma ray photons being emitted, it will tend to travel outside your body. So you want to capture those gamma ray photons that are being emitted. So if this is your patient viewed from another view right now, your annihilation occurs here, and then your gamma ray photons are going to be emitted. Your gamma ray photons, as mentioned just now, they travel in a straight line. So if your annihilation occurs right over here, let me just write here. If your annihilation occurs right over here at this spot, what you're going to get is actually gamma rays being emitted, gamma ray photons being emitted, and they travel in this direction as well as in this direction. So you want to have detectors that are placed just outside your body, usually is arranged in a ring that surrounds your patient, so that your detector can detect your gamma ray photons. Okay, so from there, that's how they're going to produce an image. All right, so how they actually produce an image is that what they want to do is that the image of your tracer concentration inside your tissue can be created by processing the arrival times of the gamma ray photons. It is specifically the time delay between your two gamma ray photons that allows the location of your annihilation due to your F18 tracer to be determined. Okay, so how they determine your image is that they want to make use of the time delay between the arrival of the two gamma ray photons at your detector. So to give you a better idea of what we mean by that, just imagine that this one is the ring of detectors that you have. And then right now, the annihilation occurs right in the middle of the ring. So when you have gamma ray photons being emitted, your gamma ray travels in this direction and in this direction in a straight line. Okay, so if it then hits your detector over here and over here, what you then want to look is the time that it took for your gamma ray photons to reach each of the detectors. Meaning to say, if I say that from here to here, it took me, say, 2 seconds, and then from here to here, it also took me 2 seconds, the time delay being 0 here. This one, let me just rewrite this. This one here, your time delay being 0 here, it will actually tell you that your annihilation occurs right at the center of your ring. Okay, so if say your annihilation doesn't occur right at the center of the ring, what you expect to see is going to be something like this. Let's just say right now you have that same ring of detectors, but this time we tell you that your annihilation occurs maybe somewhere a bit towards this side here. Okay, your annihilation occurs here, so that you're going to get gamma ray photons emitted in a straight line again, one in this direction and one in this direction. So now, if you try to look at the time that it would take for your gamma ray photons to reach the individual detectors, the one that is closer to the detector will obviously take a shorter time. So maybe this one here, it will take you maybe 0.5 seconds. And then as for the other one, it will take you 1.5 seconds. So right now, you can see that there's actually a time delay. The difference between the timing is actually 1 second. All right. So based on this time delay here, it allows your detector to determine where the annihilation occurs. In the case that you have a time delay of 1 second, it will actually tell you that your annihilation occurs more towards this side of your ring. Okay. That's how they actually make use of the time delay between your gamma ray photons arriving and your detector to determine the location of annihilation. Okay. That's how they actually use the tracer to produce your image. Okay, now for the case where you're having a lot more tracer in the tissue being studied, this would mean that more gamma photons will be emitted from a particular point, and this will be represented as a bright point in your PET image. Okay, so this is the basic principle in which they use PET scanning to generate an image. Okay, now moving on to the calculation part of PET scanning. Just now it was mentioned to you that when your positron interacts with an electron, annihilation occurs to give you 2 gamma ray photons, right? So what is specifically annihilation here? Annihilation occurs when a particle interacts with its antiparticle where they are both destroyed and their mass is converted into energy. So you remember in your AS physics, particle physics chapter, there is matter and antimatter. Mean to say, if you have particle, you also have antiparticle. When it comes to antiparticles or antimatter, one of the characteristics that you have learned is that they have same mass but opposite charge. Okay, this is the characteristic of an antiparticle. They usually have the same mass, but they have opposite charge. Okay, so right now, when you're talking about the tracer in your body, you are actually emitting a positron. Your positron is actually the antiparticle of your electron. This positron is also known as your anti-electron. Okay, this is your antiparticle right now. It's emitted from the tracer that you injected into the patient's body. It then travels less than a millimeter before it collides with your electron. Okay, so right now you actually have a particle and antiparticle interacting. All right. So by definition here, your positron and electron will annihilate each other and their mass then becomes energy in the form of gamma ray photons that move apart in opposite directions. So if you want to look at it in the form of a diagram, this one is your positron. It has a positive charge. It interacts with your electron, which has a negative charge. So upon interaction, you will have annihilation and you get gamma ray photons being emitted. Okay, so from here, what will happen is that both your electron and your positron will disappear. They are destroyed in the process. They are converted straight away into photons. Okay, so in the annihilation process, both mass energy and momentum must be conserved here. Okay, since 2 gamma ray photons, this is actually one of the more important things here. Since 2 gamma ray photons were produced by an electron-positron pair, you can actually assume that 1 gamma ray photon is converted from the mass of a single electron or positron. Okay, if you remember what mass energy tells you, mass energy conservation tells you from the nuclear physics chapter, it tells you that mass can be converted to energy and vice versa, right? mass can be converted to energy, or energy can be converted to mass. So in the process of annihilation right now, your mass is actually being converted into energy in the form of gamma ray photons. Okay, so since you're talking about mass energy conservation here, there will be a particular equation that you've learned from your nuclear physics chapter. If you remember the energy caused by mass changes from your nuclear physics chapter, energy caused by mass changes can be represented by this equation. E is equals to delta mc squared, where your delta m here is actually the mass change. And then your E here is the energy produced. Okay, C is the speed of light. Okay, so right now, if you remember just now, I told you that your mass is converted into energy here. You can make use of this equation, E is equals to delta mc squared. And then after that, because what you convert to is a photon, you can also make use of the equation for photon energy. Energy of photon, if you remember, is E equals to hf or hc over lambda. So right now you want to relate both of them together. Okay, since your electron and your positron, they annihilate each other, the mass disappears and becomes photon energy. You can relate this equation with this equation, so that eventually you're getting something like this. The energy E of a gamma ray photon produced from the annihilation of a positron electron with mass me is going to be given by E equals to hf equals to hc over lambda equals to mc squared equals to mec squared. Okay, this portion here comes from photon energy equation, whereas this portion here comes from energy change, energy produced due to mass change. Okay, this is energy produced due to mass change. Okay, this is the energy of one gamma ray photon. Okay, just be careful about whether they're talking about a single gamma ray photon or two gamma ray photons, because there's a difference later on when you do your calculations. Okay, so just like before, your F here refers to your frequency of your photon, lambda is the wavelength of your photon, H is your Planck's constant, and C is the speed of light in vacuum. All right, and during your annihilation process, not only is your mass energy conserved, your momentum will also be conserved. And it's because of conservation of momentum, that's the reason why your photons produced during your annihilation actually have equal opposite momentum. That was the reason why your photons, when they are produced, they move in opposite directions in the first place. Okay. Now, if you wanted to find out the momentum of your gamma ray photon, there's this equation here that you would use, where you say that momentum is equals to the energy of your photon divided by your speed of light. There is a derivation to get this particular equation, but it's actually not required in your syllabus. But I'll just show it to you just for your further understanding. If you remember the Browns wavelength, the Browns wavelength related your wavelength with your momentum, where lambda is equals to h over p, right? Correct? Then after that, right now, if you look at the energy of your photon being E equals to hc over lambda, so you want to relate both these two equations together. If you relate both of them together, that's how you got P equals to E over C. So what you could do here right now is that if this one is equation number 1, and then this one is equation number 2, if you were to sub equation number 2 into 1, you get E equals to hc over h divided by p, which in turn becomes hc p over h. The h will cancel each other off, so that eventually you're going to get E equals to pc Then after that, if you rearrange it, you're going to get P equals to E over C. Okay, so this is how they actually got this equation. It's actually from something that you have actually learned before, but the derivation isn't required in your syllabus, so you can actually don't really remember this if you don't want to. Okay,